All right, aromaticity. Aromaticity for a long time wasn't well understood. The old definition of aromaticity involves smell. Typically, if we think of something that's aromatic, we think of something that smells good, right? So the old definition used to be something that was pleasant smelling. Does anybody in here like the smell of gasoline?
Yes.
You can admit it if you do. There's some of you guys out there. So in gasoline, there's actually a small component of benzene, and so that's why some people find even things like gasoline pleasing. Oftentimes, aromatic compounds are found in a lot of plant products that are very fragrant too. However, not all pleasant-smelling things are aromatic in the sense of organic chemistry aromaticity, right? Oftentimes, esters are also aromatic. Same thing with aldehydes. So we had to change our definition. The modern definition is that it is a planar ring system with 4n plus 2 pi electrons that are delocalized. Sounds a little less elegant than pleasant smelling, but it's a lot more accurate. So what we're going to do today is we're going to talk a little bit about nomenclature, because I told you guys the IUPAC naming system was designed so that chemists around the world could speak to one another in a unified language. However, with aromatic systems, a lot of the old names have stuck around. And they are IUPAC accepted, and they're more common than not. So we do need to know some non-IUPAC names. So let's take a look at some of these. And before we jump into the weird non-IUPAC naming systems, I did want to jump into how we name these when there's more than one substituent. So if we think about a benzene ring with one substituent, we're not too worried. We just call this monosubstituted. However, with di-substituted ring systems, there's a bunch of different orientations, right? You could have two substituents that are right next to each other. So I'll call this R and R prime. You could have two that are spaced out a little bit more, so that this R prime is down kind of at the 4 o'clock position. Or you could have that R group at the 12 o'clock position, or sorry, 6 o'clock. All of these are di-substituted benzenes, and yet they are all constitutional isomers of one another. So what chemists have done is they've classified these a little bit differently. These are all di-substituted. The first one on the far left, where you've got the two adjacent R groups, these are called ortho-substituted. And oftentimes people just abbreviate it with an O. And yeah, so if you're naming it, you could say O dash something 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 as opposed to ortho. You can do it either way. The next one is called meta-substituted. And it's abbreviated little m. And then the last one is para-substituted. And it's abbreviated with a P. So typically we only deal with the weird prefixes anytime we have a di-substituted benzene ring. Otherwise, we go with a numbering system where we actually number around the ring. So ortho is the same as 1, 2, meta is the same as 1, 3, para is the same as 1, 4. Yeah, both of them are accepted. However, most chemists prefer to use ortho, meta, and para. Yeah. All right, let's take a look at the odd or old, however, IUPAC accepted names. So let's take a look at these benzene derivatives. First one we have is a methyl group coming off of benzene. IUPAC rules state that it should be called methylbenzene, which is fine. However, the more common name is toluene. And so most chemists will refer to anything with this sort of pattern as a toluene derivative. The next one over should be hydroxybenzene. However, most chemists don't like calling this hydroxybenzene. Instead, they'll call it phenol. So do you guys remember covering this with alcohols, right? The next one we have is the ether derivative. And I'm just going to actually have this as a methyl group, sorry. This is called anisole. So anytime you see branching coming off of this benzene ring, we call it a something substituted anisole. Next one we have is benzoic acid, where we've got a carboxylic acid coming off of a benzene ring. We've got a few more. You guys know this one. What's this one called? Benzaldehyde. You guys made this in lab? Next one we've got is a little bit different. Instead of an aldehyde, we actually have a methyl ketone coming off. This group is commonly called an acetate group. All right? And so what we call this is acetophenone. Not very intuitive, but the old name stuck. And then the last one, see if anybody remembers this. Does anybody remember what this derivative is called? Styrene, right? It's one of the big monomers in polymer chemistry. So these are commonly referred to as parent names. So anytime you see these involved in an aromatic system, these are going to be the root, just like hexane or pentane would be the root for a linear alkane, right? These are going to be the parent names anytime you see these in a substituted benzene system. So let's take an example of this. Yep.
Acetophenone, is it ACT?
Yes. If I can spell better, acetophenone is ACE. Sorry about that. My brain sometimes just gives up when I'm writing on my tablet. All right. Let's take an example one and we'll try to name it. Do we have any AC/DC fans in here? Anybody? No? Oh, gosh. What's the parent in this system? Toluene, right? If we look at it, we've got this parent system where we've got this toluene group, and then we can go through and we can number this, and we can go essentially 1, 2, 3, 4, 5, 6, right? So if we name this, we could call it 2, 4, 6 trinitro toluene. Because I'm TNT, right? TNT. So that's where the name TNT comes from, is it's just the abbreviation for 2,4,6 trinitrotoluene. It doesn't sound as good to say 2,4,6 methyl benzene, right? 2,4,6 trinitrotoluene sounds a little bit better. Do you guys want to try another one? Yep.
How do you know to put the one at the methyl group? Like, how do you prioritize numbering?
So the number one position is always at the branch that is that parent position. So for example, if we look up here, they're all mono-substituted, which means if we number them, that would be 1, this would be 1, that 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 would be 1. So the substituent coming off of your parent is always going to be position 1. Yeah.
When do we use the ortho method?
Yeah, let's take a look at a different one. So we've got this compound now, and we need to name it. And there's actually 2 acceptable IUPAC names. What's the parent going to be? Benzaldehyde. We could go through and we could say 1, 2, 3 chlorobenzaldehyde. That would be fine. What would the other acceptable name be? What would it be? Not quite. Para is when you've got things oriented opposite sides of the ring. Meta. All right, so you could call this M-chlorobenzaldehyde.
Would you accept either one?
Either one would be fine. But one thing I did want to point out was, do you guys remember when we were talking about this reagent? Yeah, it's a proxy acid. So the parent for this benzene would be a proxybenzoic acid. And where's the chloro substituent located? Yeah. So this would be meta-chloroperoxybenzoic acid, also known as MCPBA. That's where that little M comes from, as it indicates the position of the chlorine coming off of the ring. What's that? Everybody looks really upset by this. I don't know what's going on.
Different, like, of the base parent name, like 2 different substituents that are both different base parents.
So you're saying, what if you have essentially, you could identify 2 parents on one? That's a good question. So if you have 2 parents and you're unsure of what to identify, there are obscure IUPAC rules. However, I wouldn't get too worked up about them. In general, when I give you guys naming, I'll only have one main parent that you should focus on. All right, so now the question is, do we have enough time to continue on? And the answer is probably no. So I think we're going to leave the definition of aromaticity until tomorrow.